Let's pick up in this section with where we left off with quadratics from the previous section. So we had done the square root property, we had done completing the square, and if you were following along the PowerPoint, you might find that there was one slide that I didn't use. I wanted to save it for this to give you a little motivation as to why we might need another method to solve quadratics. So here's an example that involves the use of the internet in Western Europe. The figure shows a scatter plot of online users in Western Europe together with a graph of the function that models the data. So you notice it starts here in 1996. That's why there's this break over here that indicates that there's a number of years missing. From 1996, we head over to the right. So 96, 97, 98, 99. This would be the year 2000, 2001, 2002, 2003. So in those first years that the internet was spreading across Western Europe, it was doing so pretty quickly. The y-axis gives us internet users in millions. The location that I got this from has already figured out, by using computer and other techniques, that this is the quadratic that models that data. Now, you notice one thing is that those numbers are not nearly as pretty as we were hoping, right? If it was like 1, -5, and 2, that would be nice and easy to work with, but real-life data doesn't always come that nice. So the first question says evaluate f of 10 and interpret the results. So what I have to do is I have to put a 10 in for all the x's. So I get 0.976 times 100 minus, if I multiply this by 10, I get 46.43 plus 0.238. I'll grab a calculator, you grab a calculator, and let's see what we come up with. All right, when I grab my calculator and throw it in, I get 51.408. So 51.408 is f of 10. What does that mean? Well, if the function tells me the number of millions of users, then 10 years after 1990, right? It says x is the number of years after 1990. So 10 years after 1990, there were 51.4 million users. So 10 years after 1990, another way is saying 2000. So here we are in 2000. Is it reasonable that the answer is 51.408? Yeah, right? Because here's 50. A little above 50, that's what I get. The second question says, use the graph to estimate the year when the number of internet users reached 85 million. Here's 90. Here's 80. So halfway between would be 85. So what year does that happen? Follow this across until we hit a point on the data plot. And there it is. What year is that? 2002. Now, the third question says, set up an equation to solve part B numerically. In other words, rather than just looking at the graph and saying, I think it's 2002, is there a way that I can solve for x with an algebra equation? Well, I'll go back to this f of x, replace f of x with an 85. So I want to know when it's 85 million users. So 85 equals 0.976x squared minus 4.643x plus 0.238. Well, what methods have we learned so far? One of them was the square root method, and that's not going to work here because that square root method only works if there's no middle term. We had also done completing the square, which is a possibility, but remember we'd have to start by dividing both sides by 0.976. So I wonder if there's another way that we could solve a quadratic equation. And sure enough, there is. It's called the quadratic formula. So the quadratic formula can be used to solve any kind of quadratic equation, even if the answers are not real. So, are you ready for the quadratic formula? Here it is. First of all, it works if ax squared plus bx plus c is equal to 0. So we got to put that equation in a form that's set equal to 0. If that's the case, then x equals, I call it the opposite of b. I mean, you can call it negative b, but if b is already negative, the opposite of a negative is positive. So I'll often call it opposite b. Plus minus means that there's two solutions. Square root of b squared minus 4ac. And then I usually say all over 2a, meaning that this entire thing, including that opposite b, gets divided by 2a. You can look around. There's lots of quadratic songs. One of my favorites is the one that goes Jingle Bells. But you can find other quadratic songs too if it helps you to memorize. But yes, you do need to memorize the formula correctly before you start the problems. The first example, I'm not going to go through line by line because I spent all the time to type it up. It's on the PowerPoint. we can take a look at it and see how it works, and then I'll work through some quadratics that we can solve in real time. So you notice the original question was x squared minus 4x plus 3 equals 0. So a is 1, b is negative 4, c is 3. How does it go? Opposite b. So if b is already negative, opposite of a negative, positive. So opposite of negative 4, positive 4. Plus minus the square root of b squared, right? So again, if b is negative, you got to square that negative also. B squared minus 4ac. I'm putting the ones in right now just to remind you that sometimes a is not 1, in which case you're going to need a value there too, all over 2 times a. Set it up first and then simplify it a little bit at a time. So you notice I worked on the radical expression first. 4 squared is 16. 4 times 3 is 12. Once I got a 16 minus 12, I replace it with a 4. Then I simplified the square root of 4 as 2. And now I'm at the point where I'm ready to break this apart into 2 pieces. One of them is 4 plus 2 over 2. The other is 4 minus 2 over 2. So evaluate the whole top. Evaluate 4 plus 2 and get 6. Then divide it by 2. That's one of my answers. 4 minus 2 is 2. Divide it by 2. That's my other answer. So my 2 final answers, x equals 3, x equals 1. You can put them both back into the equation, and they'll both work. All right, this is where I'm getting my list of problems from. Obviously, not enough space on this slide to solve it, so I'll pull the whiteboard out, and we could work on some of these problems there. You might want to keep that formula nearby as we go through these, because they're all going to be based on knowing that quadratic formula. All right, so the first problem that was on our list to solve was x squared plus 4x minus 7 equals 0. So it might help to list out those a's, b's, and c's so that we can reference them as we go through the formula. A is 1, b is 4, c is negative 7. So the quadratic formula says x equals the opposite of b, so the opposite of 4 is negative 4, plus minus the square root of b squared minus 4 times 1 times negative 7, right? 4 times a times c, all over 2 times a. Let's work our way down. It'll take us a few steps. Let's keep this in order. Negative 4 plus minus the square root of 16. Now, I got a negative and I got another negative. 2 negatives make a positive. 4 times 7 is 28. Okay. Keep going to simplify that radical first. Negative 4 plus minus the square root of 44. But I can simplify the square root of 44, right? Square root of 44 is the same thing as square root of 4 square root of 11. 2 square root of 11. So I can write this as negative 4 plus minus 2 square root of 11 over 2. Now, I can actually simplify this a little bit. Look at the numbers that are outside the radical. Look at this number that was our opposite b. Look at this number down the bottom. They all have a common factor. I can take a 2 out of everything. Negative 4 divided by 2 is negative 2. When I take that 2 from the square root of 11, I'm left with just the square root of 11. And if I divide the bottom by 2, I just get 1, which means that the fraction goes away. And here's my answer. So you can simplify things that are in front of those radicals. You can't take values out of the radical, because inside the radical, outside of the radical is not equivalent. And here's my answer. Negative 2 plus minus the square root of 11. There's 2 answers. One of them is negative 2 minus the square root of 11. The other is negative 2 plus the square root of 11. All right, let's take a look at the second one that's on my list. Hey, for this one, I've got 3x squared minus 9x equals negative 2. First thing is move that 2 over to the other side. So I get 3x squared minus 9x plus 2 is equal to 0. Line up my a, b, and c. A is 3, b is negative 9, c is 2. How's the formula go? Opposite b, so the opposite of negative 9, plus minus the square root of b squared. So again, that negative 9 goes in the parentheses, square on the outside. B squared minus 4 times a times c, all over 2a. Remember, the a is not 1 here. A is 3. All right, let's spend some time simplifying this. Opposite 9 is 9. Negative 9 squared is 81. 4 times 3 is 12. 12 times 2 is 24. 2 times 3 on the bottom is 6. So I get 9 plus minus the square root of 57 over 6. And at this point, there's nothing else I can do with this. I can take a 3 out of a 57, but that doesn't help. That's not a perfect square. Other than that, there's no other factors I can use to simplify. So this is an answer that's an exact value. If you start turning these into decimals, now it's not an exact value anymore. So if you want an exact value that's simplified, there it is as an exact value. All right, let's take a look at the next one. The next one on my list looks like this. It's 3x squared minus 6x plus 3 equals 0. Now, you can run through the quadratic formula with the 3's, the negative 6, and the 3, but it actually turns out that both sides are divisible by 3. Well, I should say everything on the left side is divisible by 3. Clearly, 0 is divisible by 3, yes. So on the left side, I end up with an x squared minus 2x plus 1 equals 0. In this case now, my a is 1, my b is negative 2, and my c is 1. So x equals the opposite of b plus minus the square root of b squared minus 4 times a and c are both 1, all over 2 times 1, which gives me 2, plus minus the square root of negative 2 squared is 4, minus 4 times 1 is 4, all over 2. And a funny thing happens. What's under the radical becomes a 0, right? Under here, 4 minus 4 is just 0. So when I go to give my answer, that radical piece disappears completely. I end up with 2 plus minus 0 over 2. Answer is just 1. That means there's only one answer. Yes, that means there's only one answer. So this graph is going to come down, touch the axis, turn around, and go up. It's no different than when we had factored something and we got the same factor twice, and we said, well, there's just one answer. That's my answer. All right, the last example that was on that slide, I want to do this to show you what it looks like. Suppose you had a question like this: 5x squared equals negative 8. Now, if you look at this, you realize that this thing doesn't have a real solution, because you're saying that something squared equals a negative number. So the solution to this is not a real number. What does it look like in the quadratic formula? Well, if I move that 8 over to the other side, I get 5x squared plus 8 equals 0. So a is 5, b is 0 because there's no x term, and c is 8. So when I go to set up my formula, I get x equals opposite b, which is just 0, plus minus the square root of b squared minus 4 times 5 times 8 all over 2a, which gives me plus minus the square root of 4 times 5 is 20 times 8 is negative 160 over 10. What's going to happen is you're going to end up with a negative number under the radical. When you end up with a negative number under the radical, that's how you know it's a non-real solution. So we can actually simplify this, right? The square root of negative 160 is the square root of negative 16 times the square root of 10. And so that gives me 4i square root of 10 over 10, which I can make plus minus 2 square root of 10 times I over 5. So we'll get into some more examples in the next video about what happens when there's negatives under the radical, but I at least wanted you to see here what it looks like with a problem that was very clearly something that doesn't have a real solution. What does it look like when I throw it in the quadratic formula? Turns out I end up with a negative number under the radical. All right, let's go back and take a look at one more thing from this unit, and that is we had a problem at the beginning that dealt with internet use. And we had said we wanted to find out what X was when the number of internet users was exactly 85 million. So we have kind of an estimate from looking at the graph, but can I pinpoint exactly when that happens? And so it looks like this is a good opportunity to use the quadratic formula. Will it get a little bit messy? Yes, because of the decimals. So clearly we're going to need a calculator to solve this one. But the quadratic formula helps us to solve these application problems. So this was the equation, right? 85 equals so forth. First thing is subtract an 85 from both sides. Because if I want this set equal to 0, I've got to get rid of an 85. So I get 0.976x squared minus 4.643x. And then if I do 0.238 minus 85, I get minus 84.762 equals 0. So yes, my A value is 0.976. My B value is negative 4.643. And my C value is negative 84.762. This is not something that's going to give us an exact value. We're going to use our calculator to come up with an approximation in order to figure out what the answer is. So let's set this up. X equals the opposite of B, so 4.643 plus minus the square root of B squared. So if I take 4.643 and square it, I get 21 now. How many decimal places do you keep? The formula has 3 decimal places in it, so I'm going to keep 3 decimal places in my work. I can't be any more accurate than the question. So 21.557 is my B squared minus 4 times A times C all over 2A. So all over 2 times 0.976. Now, as I work through this problem, I'm going to simplify under the radical first and work my way from there. So if I throw this all in my calculator, 21.557 minus, in parentheses, 4 times 0.976 times negative 84.762, I come up with 352.468, then take the square root of it. All right, so I just copied this over from the other board so we could see step by step what we're doing. So I told you when we did the b squared minus 4ac, we got 352. So now I got to take the square root of that number. So I get my calculator again to take the square root of that number. Square root of 352.418 gives me 18.773. Over 1.952. Now, one of these is going to give me a positive number, one's going to give me a negative number. I'm talking about years after 1990. So clearly if it's going up, the years before 1990 were not real good for internet usage in Europe. It wasn't good for internet usage anywhere. So let's choose the X value that makes this positive. So let's do the 4.643 plus. 4.643 plus 18.773 over 1.952. That's the 2 times 0.976. I add the top first. All right, so let's be careful how we do this. 4.643 plus 18.773. And now divide it by 1.952. And I get 11.996. So our original estimate from the graph was that it was 12 years after 1990, in other words, the year 2002. When we solve it with the formula, we get a number that's real close to that. Okay, looks like maybe a day earlier, but we end up with 11.996 instead of 12. So that's how we do it. And the quadratic formulas that involve real-life applications can get messy because real-life applications can get messy, but yet that's oftentimes what we really need to do if we want to solve one of these quadratics to apply to a real-life situation. All right, we'll move on to the discriminant in the next video.